Hello everyone, my name is Aslihan. Welcome to my presentation. Throughout the summer, I worked with the Barcelona Supercomputing Center for the Project 5 Cross-Lingual Transfer Learning for Biomedical Text. Let's go to my project details. The goal of this research project is to provide a prototype of classification in the form of a BioSAQ submission that may take into account the Spanish language as the input, taking advantage of the extreme usage of deep learning architectures of transformers models provided by Hugging Face library. The output of the project is planned to be used in biomedical search engines and biomedical question answering systems. We can see a sample of the MISNES dataset with dash codes. Each of these annotations represents a unique identifier. We can consider the project predicting dash codes is as basically a multi-label text classification problem. The solution will be based on leveraging the power of the pre-trained Hugging Face transformers libraries. Therefore, developing a machine learning model that will accurately predict all the indexes that could be associated with the articles will provide us to enrich our purpose of the project, which is finding documents as accurately and fast as we can. And this brings such an important question, that is, how to use pre-training models for our task, or in other words, how to fine-tuning pre-trained models. The out-of-box transformers model has already been pre-trained on such a huge corpus data, and thus has a good understanding of generic on a specific language or even multilingual text. However, the particular dataset from MISNES comprises a lot of medical-related words, which the transformers models may not have seen during the pre-training phase. Hence, we need to fine-tune the model on our dataset so that it can build an understanding of our dataset and become better at the text classification task. The way to do that is to add a classification head on top of the core transformers models and then train the entire model on our dataset. We want to compare the multilingual BERT model, the beta model, with the in-house Roberta biomedical model. Basically, we want to answer the following question. To what extent a domain-specific model is better than a general domain model when making a classifier? We expect that in-house Roberta biomedical model, which is trained using only biomedical context in Spanish, will perform best among different three pre-trained models for using classification task. As we can see that we intend to find an answer to which model will perform better in cross-domain and cross-language scenarios. We use MBERT for cross-domain scenario, which is trained using 104 languages, and Beto for general domain context in Spanish scenario, which was only trained using Spanish texts, and Roberta for biomedical Spanish domain scenario, which was trained using biomedical context in Spanish texts. And when it comes to implementation after defining the problem approaches, the main libraries we need are Hugging Face Transformers library for models and tokenizer, PyTorch deep learning framework for dataset preparation, sklearn for splitting dataset and metrics, and we can list the steps as follows. In MISNES dataset, there are about 370,000 records for a training set. As a virtual health library manually indexed with dash codes that are almost 23,000 unique codes on the entire dataset. We only need abstract text and multi-label structure of the dash codes columns as an input for the training transformers models. Many of the dash codes have very low count. For the scope of this problem, we could restrict ourselves to less than the amount of the unique codes. That gives us still the same 370,000 rows of medical text, which are decent enough given that we are using pre-trained models. A histogram plot reveals that there are almost 10,000 unique dash codes that occurred in less than 10 in the entire dataset. Also, in general, reducing that many unique codes still could be reasonable for the model to be able to perform classification. Before we go ahead, we need to transform the text data into numerical representation because the models can only interpret only numerical data. We need to tokenize and encode the text data numerically in a structured format required for all transformers models. The BERT tokenizer class from the Hugging Face library makes this a simple affair. Here we can see The extracted values of the tensor of an example. Every abstract text converted into a numerical format which has attributes, and similarly every dashcode's feature is converted into a list format which is unique dashcode's length and takes value 1 if that particular example has that code, otherwise takes 0. Updating weights process is based on computed total loss for every batch after every iteration. Model weights can be modified for getting nearest score for our ground truth, which is the real label. The formula below is called BCE with logits loss, and we can see that it combines the sigmoid layer and the BCE loss in one single class. When it comes to benchmarking, we have already labeled dataset as a test set indexed manually by 7 experienced medical literature indexers, and we will use this dataset for benchmarking. And using best performing trained model, we can start predicting dashcodes that can be associated with any relevant abstract test that we have. To be able to measure the performance of the model, we can use accuracy metric as the main control metric, but we can use other classification metrics listed below to get inside more. On the sample image, we can see that the model produced prediction scores for every single class. Then using the sigmoid function, we can get predicted labels, which are dashcodes in our case. To give brief summary of what I have worked on so far, comparing different transformers model performances with different model approaches on such big data and with a huge number of labels. When it comes to obstacles and achievements I have experienced so far, even if the difficulty of the size of the label dimension, with reducing tensor's dimension into the right size, the better results we can get. And challenges, of course, the size of label dimension and memory consumption. For getting better results improving accuracy as feature improvements, we can play with the hyperparameter to improve the performance, such as the number of epochs or learning rate. And hyperparameter optimization technique could help us to be able to get the right ones we need for later training processes. And for reducing the size of the label dimension, we can also consider some clustering techniques grouping most similar labels into one label. Thank you for listening.